Hi, I'm Doug Sparks. I'm happy to be here to talk about 3D printed sensors for harsh environmental applications. Just kind of a brief outline, I'll be talking about the corrosion, pressure, and temperature challenges for sensors, particularly additive manufactured sensors. A little bit about the failure modes we've seen with conventional MEMS devices and some of the solutions. Talk about Liga, which is an older technique that is still being applied for 3D printing. Then how additive manufacturing has been initially applied in industrial sensors, how it's been applied to medical implants, and then finally the convergence of 3D printed MEMS wafers with traditional MEMS processing techniques. Now, some of us might be familiar with some of the failure modes you see when using a silicon device or microfluidic structure. You'll get diaphragm rupture, wall or tube rupturing, chip detachment as epoxy or solder is attacked by corrosive fluids. This can happen over time with hot, prolonged high pressure fluid exposure, or because of the poor fracture toughness of silicon and glass. Tubes can just rupture during a pressure spike, for example. Some of the solutions to this include the use of silicon oil immersion with a corrugated metal diaphragm in the case of pressure sensors. You might use pressure snubbers in line to knock down the pressure wave. You can apply strain gauges to tanks and diaphragm walls opposite the corrosive fluid side of the structure. So these are some of the conventional methods that have been used to enable us to still use silicon, piezoresistive, and other technologies with harsh environments. Packaging was one of the first applications for additive manufacturing. I think in the 1990s, I was making models of sensor packages using additive manufacturing. We used them for cavity pressures. An example of a medical lure set plastic package is shown here. It's been used in microfluidics for microfluidic channels. And with metal inserts, you can actually use 3D printing to make prototypes for industrial or automotive devices with a good, robust mounting bracket capability. Industrial Coriolis mass flow and density sensors that use resonating tubes was one of the first attempts that I made to apply 3D printing to the industrial environment, where you have corrosive fluids that require specific alloys to stand up to. And so on the left here is a laser, an assembled conventional Coriolis mass flow meter, which can be quite large and fairly small. All of these assembly steps can be encompassed in one 3D print to make a discrete sensor. The sensor will not only have the resonating stainless or titanium tube, but it can have the flanges or the threaded fittings. You can have additional features to attach electronics as well as a housing, all in one 3D print. And then furthermore, I've kind of built on that to even be able to print extremely small resonating tubes for this application, which I'll talk more at the end of the speech with regard to printing MEMS wafers. 3D printed orthopedics is another application, and I consider this a pretty corrosive environment. Bodily fluids are like a brine or saline solution. They can be printed from biocompatible materials like titanium. You can have a rough surface in the print, which is a pretty normal texture when you're using powder printing. And this can promote cell growth, and it can be customized. And you can build upon this with some of the techniques we've already developed for implantable MEMS devices. Here's some examples of both polymeric and titanium stents that have been 3D printed. Like I said, these can be exposed to saline solutions, to blood leukocytes. To see what the interaction is, you're going to have to do a whole battery of biocompatibility studies, medical device implant studies for a Class 3 FDA approval process. But however, this work's been going on, and it will continue to move forward. Now, let's talk a little bit about what's the smallest feature size that can be printed in 2022. You've got a variety of electroplating techniques, borrowing on Liga. You've got some photopolymeric techniques for polymers. You're getting down into the sub 10 and even 1 micron feature size with these methods. So there is promise here to make some extremely small printed structures. As I mentioned, this has been done in the past with Liga. This is using a photoresist mold and electroplating a variety of platable metals. I was most involved with nickel and nickel alloys for a resonator project that was actually developed on top of a CMOS wafer. So you could 3D print, essentially 3D printing on top of a CMOS wafer. But there were some things we learned. It took, I think, about 7 or 8 years to get to the point where we could make an automotive robust device that would pass PPAP and all the reliability testing. There were problems with drop test and shock because the initial plated material was soft. We had work hardening, cyclic fatigue issues. We had to use some alloying to increase hardness and robustness. And then the material was ferromagnetic, so we had to shield it with mu metal. So there's a number of things that we can learn from our lessons in Liga, apply this to 3D printing now. Now, this kind of shows you the progress of silicon wafer diameter over time. Most MEMS wafers now are printed with 200 and 300 millimeter diameter wafers. And one of the things that we all admire about the semiconductor industry is the Moore's law and the constant shrinking of dimensions. You know, we're down now to the 3 or 5 nanometer node space. That's something that'll be hard to duplicate with 3D printing. And so what I've proposed is to merge the two together. On the left are some of the 3D printed MEMS wafers that I've done with polymers and metals, 3-inch, 4-inch, 5 and 6-inch diameter wafers. So by being able to print a planar wafer, we can leverage this existing lithography techniques that have been developed over the decades for semiconductors. And 3D printing has some really amazing capabilities when it comes to what you can print in one session. You can print an array of tubes, cantilevers, diaphragms, cavities, all at one print. That would take hundreds of steps to accomplish this with conventional deep reactive ion etching, lithography, wafer bonding techniques with silicon or glass. So by 3D printing the substrate, getting all of your mechanical structures formed in a print, you're saving hundreds of steps, lots of time, lots of development, and then you can do your film processing on top of that planar substrate. After dicing of the substrate, if you plan your design correctly with regard to packaging, you can have robust package features made into each chip. On the left here, I show some of these tube structures with male tube ports coming out of the chips, out of the side. You can have male and female tube structures in the bottom of a chip. On the right here, this was a female recess in which we inserted stainless steel tubes that can be laser welded in place. And you can make a very robust sub-package using this 3D printing techniques. It's going to be burst resistant. There's no epoxies. There's no glass, for example. There's nothing that has poor fracture toughness in the entire chip through package fluid pathway. And then just to show you how you can put patterned films on top of the surfaces of these metal wafers. You can use CVD deposition techniques for dielectrics, for piezoresistors, for metals, for piezoelectrics. Pattern them with conventional spray on or spin on if you're clever in the way you design your wafer techniques. These can be pressure sensor diaphragms, as is shown on the left. You can put strain gauges on Orthopedics, as shown on the bottom left. And then you can assemble a very conventional pressure sensor or other type of fluidic device. So in conclusion, I'm proposing to this group that 3D printing, additive manufacturing of a variety of materials, stainless steel, superalloys, titanium, can be used to both reduce the process complexity of a MEMS device or sensor. If you 3D print the structure with all these complex surfaces and three-dimensional features, you can then put that into a MEMS fab that allows you to process metals. You can get all the lithography advantages of conventional semiconductor processing. You can add that to the material diversity that can be 3D printed. And then you can come up with a new product, an additive micro-manufactured wafer, chip, and device that can be customized and is ideal for harsh environments. Thanks. Some of my contact information is below, and I hope to talk to you soon. Thank you very much.